Exactly. Exactly. So just as I was saying, the thickness of the rod, this is the answer that the change in thickness of the rod, that is the answer that we are going to be getting. Better still, if you want to write this in a different form, it can also be written. Okay. But just make sure that whatever you are doing at the end of the day is going to be equal to the standard or experimented value. Okay. Someone could also choose to write his answer in this form. Okay. Someone could also choose to write his final answer in this form. That is 1.1.5. Okay. Times, let me say 10 exponent -3 millimeters. -3 millimeters. Exactly. Yes. So uh, that is the end of our problem 2. Okay. Straight away from here, we are going to be looking at the volumetric strain. But before that, I want to quickly use 2 pages to show you a review of wherever we began to wherever we have gotten to. Okay. Yes. So for the first one, this was problem 6.1, which we solved so nicely. So this was actually problem 6.1, and that was the first thing we did. Okay, yes. So this was problem 6.1. So that is it. Let me quickly use 2 pages so that you can. Yes, so that is it. That is it. That is it from wherever we started to. If you want to take some screenshots, quickly take them. Quickly take them. That is it. This is where we began. So where we have gotten to now. Okay. So where we have gotten to now. Exactly. So without talking much or beating about the bush, let's quickly proceed from volumetric strain and see how more we can become history. Okay. So that is it for problem 2. But before then, is there anyone having any question he or she wishes to ask before we proceed? Please, is there any question anybody wishes to ask before we proceed? Exactly. Okay. So for volumetric strain, first of all, you want to look at the proof of the volumetric strain. Okay. Yes. So we are looking at volumetric strain, just as I just said, and our main focus. That is, we are saying that take note when a member is subjected to stresses. When a member is subjected to stresses, it undergoes deformation in all directions. When a member is subjected to stresses, it undergoes deformation in all directions. Hence, there will be change in volume. There will be change in volume. Good. Let me take it one last more time again. When a member is subjected to stresses, it undergoes deformation in all directions. Hence, there will be change in volume. Good. The ratio of the change in volume to original volume is known as the volumetric strain. So just as you can see, this is the formula for volumetric strain over here. Okay. Yes. And the formula for volumetric strain. The volumetric strain is denoted as the change in V over the original V. Okay. So mathematically, that is how the volumetric strain has been expressed. Okay. So mathematically, we are saying that our volumetric strain is equal to the change in V over the original V. Okay. So where we are saying that this delta V is actually the change in V, and then when you see V is actually the original thing. Please, and a very big please, I want each and every one of us to take note that change in volume, change in volume is equal to final volume minus initial volume. So this is it over here. Your change in volume is equal to the final volume minus what? Initial volume. So this is it. The change in volume is equal to what? It's just the final volume. That is the V1 minus what? Original volume. Okay. Yes. Final volume minus the what? Original volume. So V1 is your final volume, and then the VO is your original volume. Okay. since we are still talking about volumetric strain, that is why you are still seeing it over here. And we continue to say that in this section, we shall derive formula for volumetric strain of different sections subjected to a system of forces. Volumetric strain will be considered for the following cases. That is, in case 1, volumetric strain of rectangular bar subjected to a uniaxial force. And that is in case 2. We are going to look at volumetric strain of a rectangular bar subjected to forces in 3 mutually perpendicular direction. And in for case 3, we are going to look at the volumetric strain of a cylindrical rod subjected to a uniaxial force. Please take note that volumetric strain will be considered for the following cases. Good students should have a pen, a paper, and a calculator beside them so that they can be able to jot down some of these important things that I'm actually wasting time making more emphasis on. Okay, I said that for the case 1, we are going to be looking at what? The volumetric strain of rectangular bar subjected to uniaxial forces. And also for case 2, we are going to look at volumetric strain of rectangular bar subjected to forces in 3 mutual perpendicular direction. And for case 3, we're going to look at the volumetric strain of a cylindrical rod subjected to a uniaxial force. Good. Let's look at the case 1. Then later we're going to look at the case 2. We're also going to look at the case 3. Okay. So for case 1, we are saying that volumetric strain of a rectangular bar subjected to uniaxial force. And this is what we are actually focusing on in our investigation. So 1, consider a rectangular bar of length L, width B, and depth D, which is subjected to an axial load P in the direction of length as shown in the figure below. Okay, so this is the length, this is the breadth, and this is the depth. Okay, so finally, this shows that this is a symbol for volumetric strain. Don't get confused. And for the volumetric strain, it's equal to the X, okay, plus the strain at Y plus the strain at Z. Okay, our volumetric strain in this case shows that our volumetric strain is equal to the strain at X plus the strain at Y plus the strain at what? Z. This is the axis we are making reference to. So don't get confused. And that is, let delta L be the change in length, delta B is the change in width or breadth, and delta D is the change in depth, as we all know, as we have been saying so far. And this, I want you to take note that the final length of the bar is just equal to the original length plus the change in length. And also the final weight is the original breadth plus the delta B. The final depth is also equal to the original depth plus the what? Delta D, as simple as that. Okay. So this is a proof of the formulas. Let's also say a little bit about the case 2. Okay. But even before anything, I want you to, this formula we already know. If you're able to write it again, it will help you. And also this formula, I want you to put this formula somewhere. Okay. Yes. So after the proof, this was what was discovered, and we realized that our volumetric strain is equal to what? The change in length over the original length multiplying 1 minus what? 2 mu. Okay. So that is it. And also, I want you to keep this formula too somewhere. We'll make more emphasis on it later. Okay. So let's quickly look at the case 2 too. But before then, is anyone having any question to ask before we proceed? All right. So for case 2, we said that we want to look at the volumetric strain of a rectangular bar subjected to a force in 3 mutually perpendicular direction. Good. Consider a rectangular block of dimension X, Y, and Z subjected to 3 direct tensile stresses along 3 mutually perpendicular axes as shown below. And this is it as you are seeing over here. You can see Y to Y, you can see Z to Z, and you can see X to X. Okay. It's all about So you can see it over here, and this will show that our hot volumetric strain, okay, for in this case, our volumetric strain, the formula that we can use to get the volumetric strain is also is equal to what? 1 over elasticity times what? The stress at x plus the stress at y plus the stress at z, all multiplying y minus what? 2 mu. So I want you to also put this formula somewhere. And then the proof of the formula that I'm talking about led to this. Okay, so this is the proof of the formula. We are not actually focused on that. So you have to keep this formula somewhere. This is the formula I just spoke to you about. If you want to prove the formula now, you realize that it's going to take a lot of time. Okay. But for our study, we just need the formula to be able to understand the question and then solve to get the answer. Yes. So that this is it. So for the volumetric strain in for case 2, this is the formula we are going to use. Okay. Uh-huh. Um let's quickly go through these special cases. We are still under the case 2. Okay. We are still under the case 2. And since you're under the case 2, let's look at these special cases. If load is applied in only one direction, it implies that the stress in the other two direction will be 0. If load is applied in only x direction, equation 6 becomes this. That is, volumetric strain is going to be the stress at x all over E multiplying 1 minus what? 2 mu. Okay, so it proceeds like that. If it's as y2, that is it. If it's as z2, that is how it will look like. Good. So let's just quickly look at the case 3 and see if we can be able to solve some questions since we are already caught up by time. So for the case 3, we say we want to look at volumetric strain of circular bar subjected to uniaxial force. Volumetric strain of circular bar subjected to uniaxial force. And for those ones, the formula that we can use to calculate for them is this. That is, the volumetric strain is equal to the change in length over the original length minus what? 2 delta D over the what? Original D. Okay, so consider a cylindrical rod which is subjected to an axial tensor load P. So these are the loads, and I have explained this diagram somewhere already. Yes, so you can see the original length and also the change in diameter and also the original diameter as well. Okay, we are saying that let D be the diameter of the rod and L be the length of the rod. After so many proofs, you realize that we were able to establish the formula that I showed you. So you can also put this formula somewhere. That is for a hot. That is for the case 3. And that is for case 3, which we are saying that volumetric strain of a circular bar subjected to uniaxial force. Okay. And case 2 was about what? Case 2 was just simply, let's all go and look at it. Case 2 was just about volumetric strain of rectangular bar subjected to forces in 3 mutually perpendicular axes. Okay. Finally, let's look at what the case 1 was also about. And the case 1 was the volumetric strain of a rectangular bar subjected to uniaxial force. You see. So since case 1 was rectangular bar, you realize that case 3 is what? Circular bar. Case 2 is just 3 mutually forces. Okay. So that is it. That is it. That is it. As simple as A, B, C. So let's so from here we can just start looking at some work examples, and I believe that that will enhance your understanding more than the formulas we are looking at, because I realize most of you are actually getting confused. Before we proceed, I want to take some one or two few questions before we solve our first problem on volumetric strain. So is anyone having any question to ask, any contribution before we proceed? Any contribution, any question before we proceed? Okay. Since there is no question or contribution, then we just have to proceed. Okay. So let's pick our first example. That is example 6.3. Okay. Better still, if you wish to, we could solve some of the trial questions. But let's solve one of this, and then later we will take one of the trial questions And I believe that is going to be very, 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 very good. So let's just solve example 6, question 6.3, and let's see how to go about it. The question says that calculate the change in volume of a steel bar of 20 mm diameter and 600 mm length when a tensile stress of 180 Newton per millimeter is applied to it along its longitudinal axis. Take E to be 205 gigapascal and then the Poisson ratio to be 0.3. Still telling it that it is a steel. Without talking much over here, let's start, and that is our problem. Problem 6.3. Okay, so this becomes our problem 6.3. And problem 6.3, first of all, we have to start with our given. So this is our given. Let's quickly put down the given and see how best we can all become history. So let's proceed. And that is, our question is saying that calculate the change in volume of a steel bar of 20 mm diameter and 600 mm length. Okay, so the change in volume. So this is it, change in volume. This is equal to what? Change in volume, which you don't know. So change in volume. And the change in volume is equal to, we don't know. Okay, and then so the diameter. Our diameter, so I'm sure we don't know the diameter, or it was given. Okay, so the diameter was 600 mm. Okay, yes, 600 mm. So that is 600 mm. Exactly, exactly. So this is the diameter, 600 mm. And then the length of the bar. Okay, so the length, our length is equal to the L. Okay, and then we know that, so this was actually 20, and then the length is 600. Yes, so the diameter was 20 mm, and then the length is equal to 600 mm. Good. So let's proceed. When a tensile stress of 180 Newton is applied to it along its longitudinal axis. So let's put the tensile stress. So this is the tensile stress. So tensile stress. So these are tensile stress. So our tensile stress is equal to, and the value was 180 Newton per millimeter squared. So 180 Newton per millimeter squared. You see? So that is it. Okay. And I'm supposed to take our Poisson's ratio. You have to put down the given, or else you lose marks. Okay, so this is it. That is the tensile stress. Just this is tensile stress. And the elasticity. Elasticity. So the elasticity over here was given to us as what? 205 gigapascal. Okay. And this is the same as our E. But if we want to reconvert this, then we can write it to become this. Okay, and that is this, what they have given to us over here is the same as what? 200, or let me say 205 times 10 exponent 3. 205 times 10 exponent what? 3 Newton per what? Millimeter squared. You see, as simple as that. Okay. So finally, our Poisson ratio, let's put it down and let's proceed. So our Poisson ratio, for our Poisson's ratio, so finally, we can say that Our Poisson ratio, this was given to us as 0.3, 0.3. Okay. So if this is equal to 0.3, then finally we can just proceed to solve our work. Okay. Because we were only asked to calculate for the change in volume. So we can proceed to the solution. We can proceed to our solution since we've already put down all our parameters from the given. Let's move to the solution without wasting much time. So this is my solution. This is my solution. Okay, good. So from the solution, uh, we have to calculate for the volume of the bar. This time it's no more area. So we have to do the volume of the bar. And for the volume of the bar, we have to calculate for the volume of the bar. Okay. So the volume of the bar is actually the area times the length. Okay. So solution. First of all, we have to calculate for the volume of the bar. So the volume in this case is equal to what? Just the area times the what? Length. Area times the length. Okay. From here we can say that our volume, from here we can say that our volume is equal to, the area in this case is equal to what? Uh, because it's a circular rod, we are going to use what? Pi d squared over 4. That is the pi d squared. Okay. All over 4. Okay. Yes. Times the L. Times the L. So from here we can say that the volume of our bar, we can just do substitution. Okay. We can just do substitution to get our answer, and that is what I'm actually talking about. So from here we can say that our V. From here we can say that our V. We can say that our V is equal to 3.142, okay, times the D that was given to us, and the diameter was, what was the value of the diameter? 20. You see, so times 20 all squared over what? 4. Times the length. The length in this case is what? 600. So let's put it over there. 600 millimeters. Okay. This guy is also in millimeters, so don't get confused. So finally, when we punch this, if we punch this, we can punch it bit by bit, or we can punch it all at once. Let's do it bit by bit and see something. That is 3.142 times 20 into brackets all squared all over 4. We are going to get what? 314.2. Okay. And this is actually millimeter hot squared times 600 millimeters. So this is what brings about a millimeter cube. Because in indices, if the bases are the same and they are multiplying, we add the exponents. So finally, we are saying that what? 314.2 times 600 is going to give us 18852. Okay, 0. So finally, we're going to get 188,520. 188,520 millimeter cube. Okay. So that is the answer for our volume. Now the next thing we can calculate for is just the volumetric strain. Okay, since we already know the volumetric strain. Since we already know the volume, so we can now calculate for our volumetric strain. So over here we say that our volumetric strain, our volumetric strain we know that the volumetric strain is equal to what? The change in volume over the original volume. Okay, so let me write over here original volume. Original volume. Then if I go to the numerator, I'll just write change in volume. So over here was change in volume. Change in volume. Okay. So if I want to write that symbolically, if I want to write it in terms of symbols, then it means that my volumetric strain. Okay. So I'll just write strain and I put V over here. My volumetric strain is equal to what? The change in V. Okay. All over what? Original V. Don't get confused. So finally, what about the change in V? Do I know the change in V? Do I know the change in V? We know that this is the formula for our volumetric strain. Okay. Do we know the change in V? Ask yourself, do you know the change in V? Do you know the volume? Yes, the volume is known, but we don't know the change in V. So it means that for this formula, we can't use this formula for now. Okay. So first of all, we have to adopt the ones that we were using or the cases that we looked at. Okay. So we have to adopt from the cases that we looked at. Okay. So in that case, it means that we can't apply this formula now. And we have to apply what? The cases that we looked at, and that is a volumetric strain is equal to what? The stress over E multiplying 1 minus 2 mu. Okay, so that is the formula we will use first, even before we come and what? Look at this. Okay, because we have so many types of volumetric strain in terms of calculating for them, depending on the nature of the question, whether the question is a circular, rectangular, and all that. Okay, so the formula we are adapting for our volumetric strain. Okay, so this is over here, we're calculating for the volumetric strain. So the formula we are adapting to calculate for our volumetric strain in this case is actually what? This. And that is our volumetric strain is going to be equal to what? The stress over the what? Elasticity. Okay. Times 1 minus what? 2 mu. Good. This is the formula that we are going to use. Okay. So from here, it's just a matter of substitution. So we can say that our volumetric strain now is equal to, let's quickly do the substitution. And that is, we know the stress. The stress is 180. Okay. We know the stress to be 180. That is what we just calculated for. 180. It was even given to us. Okay, this is it, 180 Newton per millimeter squared. All over the elasticity. And the elasticity was 205 times 10 exponent 3. They all have the same units. So you see, they'll even cancel out. Okay. Yes. Multiplying what? 1 minus 2 mu. Okay. Multiplying 1 minus 2 mu. So this is it. This is it. But the mu, we know that the mu is equal to 0.5. So let's put it inside 0.3. Okay, so over here 0.3. Okay, so let's all quickly point this together. Let's all quickly point this together. Let's all quickly point this together. And if you point this, you realize that we are going to get, if you're able to point, you realize that we are going to get what? 3 point. Okay, let's all do it together. 180, okay, all over 205 times 10 exponent what? 3. Okay, all multiplying brackets open. You say 1 minus 2, open bracket 0.3, close the bracket and bring another one. You're going to get what? 3.5. You're actually going to get 3.512. Let's just leave one sign. Yes, 4 decimal places. 22 times 10 exponent negative 4. Okay, times 10 exponent negative 4. It has no unit. Okay, now that we know this, we can now calculate for our change in volume, because the question was asking us to calculate for the change in volume of the rod. Okay, so from whatever we know, since we know that what our volumetric strain since we know that the volumetric strain, okay, so since what, we also know that the volumetric strain is equal to what, change in what, V over the original V. We can just do substitution to get the change in volume. Okay, so finally we can say that the change in volume, we can use this formula to get our change in volume, and that is, we are going to multiply the volumetric strain times the what, volume. Okay, so finally let's quickly do that, and we'll see that our change in volume is going to be equal to, our change in volume is now going to be equal to 3.5122. That is 3.5122 times 10 exponent negative 4, okay, times the volume we calculated for. And what is the volume? 188,520. Okay, so that is it. 188,520. Quickly punch, everyone, let's quickly punch this together, and you realize that finally, our change in volume is going to be equal to what? 66.212 millimeter cube. Okay, yes, 212 millimeter cube. So at this point, I want to take some few questions before we wrap up for today's class. So this is where we have gotten to from wherever we began. Good students to see me in groups, in person, one-on-one, in case they find